Hello everyone, and welcome to another GIS lecture video. And in this lecture video, I want to finish our discussion on vector data by talking about this last component called topology. And the reason I want to bring up topology is because it is actually a very important concept in vector data when you start to move into real-world GIS applications, because topology has a lot of implications on both the quality of the data, but also on the underlying assumptions that different analyses are making when you try to run them. So let's talk about topology. Right. So as I said in the previous video, right, topology is just this idea that we can have a series of rules about the interactions between features in a given data set. And I think it's going to be easiest to explain what I mean when I say that by just going through a couple of examples of typical rules that topology will enforce and draw a couple of diagrams showing what it means to break those rules and what it means when those rules are enforced. So that you can get a feel for how topology works and why it's important. And I want to sort of say at the offset, and this is actually really important, right? Not all vector data has topology, right? It's a component of vector data, but it is by far the rarest. In fact, most vector data that you find on the internet, especially if you download what's called a shapefile, or a .shp, right? This is one of the most common currently methods of sharing vector data. This does not have a way to handle topology, right? I'm not going to spend too much time in this course belaboring the different file formats, but in this particular instance with topology, it is important just to be aware that not all vector data formats, in terms of file formats, will actually have topology. And some file formats, like the shapefile, which is one of the most common, literally cannot. It is impossible with that file format to keep the topology in the file format. So let's go ahead and talk about topology. Right, again, it's rules that are enforced on data to help maintain rules on the interactions between different features. Okay. So let's say that we have a road network, right? I'm going to do my best to diagram this out, right? I'm going to use slightly different colors here, right? Let's say we have the following road network. Okay. So as it stands right now, right, we have three roads. We have this gray road here. This would be 1. We have this orange road here. That would be 2. Right, and then we have this yellow road here. That would be 3. Okay. So you might look at this and you might be like, knowing very little about vector data at this point, you might be like, okay, that's great, right? This is perfect. We have some vector data. Who cares? Well, some things that you might want to be aware of is the way that we've drawn this currently, right? These two roads that overlap, right? These two roads just run across each other, right? There's nothing telling the vector data that these two roads interact in any meaningful way. And if we think about, for example, trying to use GPS on a multitude of levels, trying to use GPS, right? Something like this would be a nightmare because there's nothing telling the GPS that there's a node here for a car to be able to turn, or that these two roads are different segments for something called geocoding, which is where we take addresses and convert them to points on a map, right? So something like this would be a nightmare for a lot of GIS applications. right? Another thing to think of is to look up here, right? I know I sometimes have bad drawing skills, but I purposely left this gap here between this road and this road, right? I guess I should clarify, right? This is a road network, right? And again, right, same thing. Just think about the most useful case scenario for roads in GIS is, right, again, navigation. Now, think for a second, right? This gap here, the GPS that you're using in your car will think that you can't do this, right? There's a space here. Your car can't drive that, right? And now, sure, maybe that is a legitimate case, right? Maybe there's a dead end here. But for our case, right, we're going to assume that this is an error and that this should really be here, right? So these two things are errors. Right, and so one of the points of topology, when I said that it enforces rules on how features interact, one of the big things that topology does is it determines what would be considered an error, and it sets up rules for how to address those errors. Okay? So let's go over the two errors that I just outlined, right? These two lines crossing without any knowledge that they exist relative to each other. And this error here that, hey, this end here should be coincident with that line there. Right, so what we would do in topology is we would say, hey, topology, let's create some rules that prevent this from happening, right? That look through the data and find things and fix them. So what we would say with topology is we would say one potential rule would be, right, all lines, right? All lines must overlap at a node. So what do I mean when I say all lines must overlap at a node? What that means is, right, if we implement, sorry if I misspelled implement, right, if we implement rule 1, what will happen is, trying to draw them the same as I did before, is we will put a node here. We will break these lines up into different pieces, right? So we would have something that looks more like this, right? Where now we have a segment where this whole thing here was one line before. It didn't care that it crossed over this one, right? After we implement the first rule, right, instead we have now we have 5 pieces, right, where this right here is now an endpoint for line 1, a start point for line 2, an endpoint for line 4, and a start point for line 3, right? Where now these 4 line segments are all aware of each other. So now, right, when we're talking about geocoding, right, we can geocode properly for this section here. And for routing, right, we know that we're able to go from here to here, turn, and go along this road. Right, so by saying all lines must overlap at a node, or put another way, lines cannot overlap, right? We have to have a node here. Right, that enforces this idea that, hey, these 4 line segments now, or the original 2 line segments, right, communicate with each other. So what about this error up here? So looking at this right here, right, what the technical term we would call 3 in this case and 5 in this case, right? This is a technical term. This is called a dangle. right? Where you have a piece of a line set network, right, that should be connected to the rest of the network, but yet are not, right? Anytime this happens, it's called a dangle. And what we can do is we can implement another rule. Actually, you know what? Let me take a second here and specify the actual ArcGIS Pro names. So if you ever see them, right, all lines must overlap at a node. This is called, right, must, not wust, right? The name for this is must not, or must intersect, I should say. Must not intersect. Right? All lines must overlap at a node. The actual name for the rule is must not intersect. Basically, this right here, where they cross without being aware of each other, this is called an intersection. Right? When we say that they must overlap at a node, right, we now have multiple different line segments, so they're not actually intersecting each other, right? This node is handling, again, that communication between the four of them. Up here, right, when we have this gap, that makes this thing here called a dangle. And what we can do is we can have a rule that says, right, all lines must connect to each other. Right? And basically the way this is must not have dangles. Right? And so if we implement rule 2, right, what happens is we would have something that looks like this. Right, where now we've dealt with this here, this error, by making lines overlap at a node. And we've dealt with this issue here by must not have dangles, right? We found where they're close enough together that we put them together. And then again, right, we implemented rule 1 to make sure that this was not intersecting. So we now have 1, 2, 3, 4, 5, 6 line segments that are dealing with the fact that we had originally 2 line segments running over each other without communicating, called an intersection. And we had a line segment that was just slightly off of where it should have been, and that was called a dangle. So these are just 2 examples of what topology can do. There are all kinds of topological rules. I do want to go over one more example, just because I think it's helpful, right? Let's imagine that that you're working for a surveyor, and you go out and you survey 2 properties that are next to each other. Right, so you have property A, and then you survey again, and you have property B. Right, you have property A and you have property B. Right. So hopefully just by looking at this, right, you notice that we have this area right, actually let's do that in a different color. That you have this area right here, right, where they're overlapping. And you say, okay, well, that doesn't make any sense at all, right? Property boundaries shouldn't overlap. So what we do in this case, right, we have 2 different rules we can implement. one would be to say, right, polygons cannot overlap. Right. So this would be, right, to use the actual term, right, this is must. Why do I keep putting W? Must not overlap. Right. And so what would happen in that case, if we implement rule 1, what we would do is we would end up, let me try and do this in a slightly better manner here. What we would end up doing is we would end up actually creating a third polygon. Right, so now we would have A, B, and C. Right, so that's one option, is we can just say, hey, if they overlap, make a third polygon out of it, right? Don't actually allow A and B to overlap. Make a third polygon C that represents the area of overlap. Now, there is another that we could do where we would say that, right, polygons must have coincident, probably spelled coincident wrong, boundaries, right, must have coincident boundaries. And so what that would say is I would say, okay, this overlap is clearly an error here, right? That, let me redraw this, right? That what they're saying is, right, rather than the overlap being legitimate, but making a separate polygon for the overlap, what we're saying is that this line here and this line here are the same line, and that there must have been an error or an issue in the generation or the surveying, right? Maybe one started from a different location than the other, and by the time you got over here, there was error that introduced this gap. And so what would happen if we implemented that is we would just simply have a single line that would be shared by both. Right? This line here now, there's no more overlap, right? We've removed the overlap and said that these two lines are the same line. Right? So we still only have A and B, and instead we've just collapsed those 2 points. So these are, again, some examples of what you can do with topology. Hopefully this makes sense. I know this is a little bit longer of a video, but topology is a very important concept in terms of just enforcing things that we might assume about the everyday world that the computer doesn't, without us explicitly stating, hey, computer, follow these rules to make sure that the data that we have lines up with the assumptions that we're making about what the real world data should be. So hopefully this makes sense. And as always, if you have any questions, please reach out. Thank you.